So I will talk about my favorite problem. This has been my favorite problem for 20 years, which makes things quite personal. So I will tell you some personal things, and also, yeah, the whole talk will be a bit informal or quite informal, and some things will be quite non-precise and loose. Sometimes I will tell you more details, which I find somehow more interesting, or at least where it's possible to tell you details in a short way. Okay, so let's start with the original problem. Yeah, so the whole talk will be about the Kakeya problem. So you might think that old gentleman is Kakeya, but no, he's Bezikovich, because Kakeya didn't do too much except asking the following problem, which is now called Kakeya needle problem. My handwriting is quite awful, so if you cannot read something, it's not your fault, but my fault. So please let me know if something you cannot read. So Kakeya asked this almost 100 years ago in 1917. And this is the last thing he did, essentially, about the whole stuff. So his question was the following. Okay, so first I tell you and then I ask. So we have a needle like this in the plane, and we want to rotate it 180 degree or 680 degree, and we want to do it so that the total area which is needed is the smallest. So let me write it more precisely. So he asked, what is the minimum area of region in the plane in which a needle of unit length can be turned through 380 degree. And I don't try it, but I mean continuously. Okay, so it's your turn. Okay, so first, give me regions which are good. But what is the most obvious example? Yeah, exactly. So a disk of oh, I hate this system. Okay, so disk. Okay, let's draw this. What should be the radius of the disk? 1/2. Then it isn't very complicated to turn around, and then the area is pi over 4, which numerically 0.785. Okay, any idea how to improve this? Yeah, I like teasing students, so give me something. Or is it the best?
Some characteristics curve.
Yeah. Okay, it's a bit easier for you because you saw that picture. Okay, let's see something. Okay, something convex. So Kakeya also, maybe he meant the question, what is the smallest convex? And I can show you the smallest convex. The smallest convex is a very tricky region, which is the regular triangle. Of course, the side length shouldn't be 1, because then you cannot do anything, but this is 1, the height is 1. If the height is 1, then of course you can easily do the job. You just do this way, this, right? Okay, and then of course this side is 2 over root 3, so then the area is 1 over root 3, and this is 0.5 7, 7. And this is the best convex construction. I mean, this is known to be the best convex region. It was proved by Pál, Hungarian mathematician, in 1921. So not much after the question, the convex thing was solved. And actually, in the paper of Kakeya, it seems that his guess was this object. I don't know what's the name of it. And how I can show you. Yeah, this object is better if we allow non-convex stuff. So it's something like this, and its area is pi over 8. So just 1/2 of the original one. So it's 0.393. Okay, and you can see how nicely this can move around there. Okay, and so it seems that Kakeya probably expected that this is the best one. Okay, so you saw this number, this number, this number. What is your guess? What can be the smallest area, roughly? Okay, so it must be between this and 0. So let me ask, who thinks that it can be less than 0.2? Who thinks that this is impossible? Okay, so yeah, so there were more people here. So let's cut this as well. Who thinks that we can go less than 0.1? Who thinks that we cannot? Okay, so it seems that this is somewhere where the guess is. Well, I don't know how natural these guesses are, but the answer is more surprising. The answer is that there is no smallest area, and this is what Bezikovich did. So now let's go back to his face. Yeah. So this old gentleman wasn't old that time. Okay, I will write 2 dates. 1919, when he did something without. Actually, that time he lived in he lived in Russia, and he hasn't heard about this problem. But he essentially solved this, and by 1928 he was in England, in Cambridge, and then he realized that he can answer this question. So he said that arbitrary small area is enough. It's not hard to see that you cannot do it with 0 area, because if you don't visit 0 area continuously, you cannot move anything. But you can make this area as small as you wish. Okay, and I can show you a possible geometric construction, which is not exactly what he did, but pretty similar. Okay, so the idea is, okay, so take a triangle. Of course, it's enough to rotate 60 degrees. If you can rotate 60 degrees with small area, then 6 times that will be enough. So in this triangle, I can easily rotate 60 degrees. So I cut this triangle into 2, and then I shift them like this. This way the area is smaller, and still I can rotate, because, okay, so I can rotate this like this. Okay, there's a jump, which I have to explain, and then after the jump I can go on. But the jump is a parallel jump, and any parallel jump is easy with arbitrary small area. These are so-called Pál joins. So if I have my needle here, and I want to move this needle here to this parallel segment, then I can do this arbitrary small area. Can you see why? Yeah, so I move it quite far, like here, and then I slightly turn it. So now I need this area, but the smaller the further I take, the smaller the angle. So then, and then I move it here, and then again I rotate. So I need only these two areas, and these are as small as we wish. Okay, so parallel movements can be done very as small as we wish, and then we can keep repeating this. So now we decompose it into 8, and then every 2 is moved like this, and then they are moved like that, and we get like that. This is the so-called Perron tree. So this presentation, this construction due to Perron. Yeah, sorry. Oh. And then we get something like this after some points. Yeah. Beautiful picture. So you can see that there are these kind of... Okay, to be honest, I don't understand too much from this picture either, but I think it looks pretty nice. So I leave it here. Okay. So this is about the geometrical case, when a needle problem, when we want to rotate a needle continuously. But if you somehow take the limit of this, so from this arbitrary small construction, in the limit case, you get the following construction. You get a set, and this is actually what Bezikovich did in 1917. That he constructed a set. So Bezikovich in 1917 constructed a compact set of Lebesgue measure 0 in the plane that contains unit segments in every direction. Okay, so if you don't want continuous movement, just segments in every direction, then you can make this area to be 0. And in fact, this is what Bezikovich... So Bezikovich was interested in the question if we have a... So his motivation came from analysis, that he asked himself if we have a function of two variables, and we know that it is Riemann integrable in the plane, whether we can always find a coordinate system so that in that coordinate system we can take just the integrals in one direction and we integral them. And he realized that to show a counterexample he would need such a construction, and then he provided this construction and then convinced himself that the question, this analysis question, is a negative answer. Okay, so this is the Bezikovich said, and this can be constructed using this Perron tree stuff as well. But now I want to show you a completely different approach. Surprisingly, this is also due to Bezikovich, but about 40 years later. Okay, this is also Bezikovich, and I guess about 1964 or something like that. So much later. Okay, so the goal is again showing such a set, but now instead of unit segments, we want full lines. Oh, by the way, I should tell you that such a set this set is called Bezikovich set since then. And now we want to construct a Bezikovich set which is even more than that. We want full lines. So the goal is construct now a closed set, because of course compact sets cannot contain lines. Closed set B that contains of measure 0, of Lebesgue measure 0, that contains lines in every direction. Okay, and here is the idea. Okay, some notation. So I want to, so if we have 2 points, let me write this way. So if we have 2 points in the real line, then we can take a line. I denote it by LAB, which is the line y equals ax plus b. So to every point in the plane there corresponds a line. There are many ways how you can match points of the plane to lines of the plane. It doesn't matter which method we use. Actually, Bezikovich used the, what's the name of that when you use a circle? Sorry? Yeah, the polar. No, it's not polar. It's the, there are people in geometry. How do you call? Okay, it doesn't matter. Okay, so we take this, and if you have a set of points, so let C be a set of points, then we can do the same stuff. So by L of C, I will mean this, that take every possible, so for every point A, B from this, I consider this the code space. So for every point of the code space, I consider the line LAB, and I take the union. Probably it's nicer to write this way, sorry. So the union of LAB, well, AB is in C. Okay? Probably I should show you a picture or something. So here is C, which are some points in the plane, and to each point corresponds a line somehow. So this is LC. So this I consider the code space, and these are the union of lines. And the question is, what properties C must satisfy to guarantee that we have lines in every direction? And what property we should need about C to guarantee that this will be our set B, that this set has measure 0. Well, the easier is this. How can we guarantee that we have lines in every direction? Well, almost every. There will be one exception. This is easy. Exactly. So what we need, that the projection of C into the x-axis, this should be everything, because line in every direction means that we want every possible slope, so we want every A, and if we have AB here, then projection to the x-axis is exactly A. Okay? This way, if this is true, then we have lines in every direction, well, except vertical lines. But of course, one direction doesn't matter. Okay, this is easy. So this is one thing that we want about our C. And now comes something less clear, but still absolutely elementary. Okay, sorry, I will use the same picture. The following, the idea that let's fix a vertical line. So let's take the vertical line x equals t. And now, if we have the line ax, this is the line y equals ax plus b, then we can easily calculate the coordinates of this point. Well, this will be clearly the point t, at plus b. So now I want to consider, so here is my set, I want to consider this intersection. So this intersection, here the first coordinate is fixed, and the second coordinate, okay, let me write this way. So this LC intersection with this line, these are exactly the points where the first coordinate is t and the second is at plus b, where AB is just a point of C. And what is this? This is just a scalar product of AB and the vector T1, which means that this whole stuff is just a scaled copy of a projection. So this is a scaled copy of the projection of this set C to the line with slope, well, something t or 1 over t, I guess 1 over t, or something like that. Okay? So let's go back here. So when we are taking these vertical sections, these are exactly the same as if we are projecting this code set onto different lines. What is our goal? Our goal is to make this set zero measure. So our goal is to have we want almost every vertical line to have measure 0. This is the same as almost every projection of C has measure 0. So the other property we need is that almost every projection of C has measure 0. Okay, this is the second property. So if someone gives us a set in the plane with these two properties, then taking this C and taking this LC, we get a good Besekovich set. Okay? And now comes another magic that helps. Okay, let's erase this. And these are the projection. There are projection theorems which did not exist in 1919 when Besekovich did this, but they already existed in the 60s due to Marstrand. Yes. And Marstrand had many projection theorems, and a projection theorem, or rather a corollary, a surprising corollary of a projection theorem, of one of the mass projection theorem is the following. I think this will sound quite surprisingly. So let A be a Borel set with finite one-dimensional Hausdorff measure. I will define Hausdorff measures soon. For the one-dimensional Hausdorff measure, you should think as a generalization of the lengths. So we have a set with finite lengths. And now comes the, for me, extremely surprising statement that if the projection of A has measure 0 in at least two directions, then the projection has measure 0 in almost every direction. Okay, so two directions implies almost every. Okay, and then our situation is simpler because now we want a set which has finite lengths. One projection is everything, or at least big. Of course, if it's an interval, that's enough for us because then we can copy. But two projection has measure 0. Okay, now I can show you such a set. I don't know how much you know about similar sets. Surely you have heard about at least the Cantor set. So it will be something like the Cantor set. If you have heard about fractal similar sets, then this will be familiar. So let's take the unit square. And let's take the corner squares so that this, so this is 1 and this is 1 over 4. So each of them has length 1 over 4. So instead of the big one, we take these 4. And then in each 4, we take again 4 little ones. And this is 1 over 16. So this is similar like the Cantor set construction, just in the plane. And we cut out not the middle third, but the middle half. And so on. Okay, so the first generation is 1 square, the second is 4 squares, 16 squares, and so on. And we take the intersection. Okay, what we get will be our set. The set C. And what do we know about this? Well, its length, so its one-dimensional Hausdorff measure will be 1 because in every generation it can be covered by 4 to the n squares of side lengths 4 to the minus n. Okay? This implies that this has finite one-dimensional measure. And if you take these projections, if I project to the vertical and horizontal directions, then they will be measure 0 because this way we will get a Cantor set, well, not the classical Cantor set, but the Cantor set when we take out the middle half. Even when we take out the middle third, it has measure 0, So it's even more set of measure 0. And I claim that one projection is full, so it contains a full segment, and this is, I think, this projection. So the slope to projection, because if you project this way, then you can see that these 4 will fill everything. And then by induction, each generation, if you project this way, so these 4, the projection of these 4 is the same as the projection of the big one. And then by induction, the projection of each generation is the same as the projection of the big square, so you get a full segment. And of course, then taking many copies, you get the line. Okay? So we are done. So we constructed this way a Bezikovich set. So then this code set will be good, and then we get something like that. And I can, okay, now you might ask that, okay, how does it look like, this Bezikovich set? That's not hard to show. Okay, let me erase this one. That almost every projection has measure 0? No, it's not easy to show. Or no, not at all. Actually, for some time it was an open question to show, to give some elementary proof or some proof without using the projection theorem, and it turned out to be hard. It's a very good question. I think there is no other. Oh, I mean, there are some trivial ones. No, sorry. There are some. Of course, there is the orthogonal one, and I think also if you, for example, project so that this goes to here. Oh no, sorry. You want. No. I'm wrong. Then it's even smaller. No, I'm wrong. This is the only one. This is the only one where it's very big, and okay. Well, I am arguing with myself continuously, so I don't know anything for sure. The only thing what I remember that you cannot do this by hand. Well, at least maybe you can, but most people cannot do it by hand, and they couldn't do it immediately. And actually, the construction that you get from here is interesting. It's due to Kahn, and he published it with a proof. And I also presented that construction at the Utrecht University. And then when the second or third time I presented, I realized that the proof was wrong. The result was correct. And the Bezikovich set you get from that is the following. So we take this 1/4 Cantor set. Okay, so this is 0, 1 over 4, c over 4, 1, and so on. So you always cut out the middle half, and you take the shrinked copy of this, the half shrinked copy of this. Okay? And you join everything to the top, from the top to everything here. So you get all of these. Okay? Something like this. Okay? And this is a very concrete Bezikovich set. Okay. So this is how you can get a Bezikovich set, but there seems to be no problem here, and I told you that I will talk about the problem, and the problem is about, okay, so we know that we have Bezikovich set of 0 measure, and then the next question, okay, so such a Bezikovich set can be small, but how small it can be, and among the sets of measure 0, we can distinguish them according to dimension. So how small the dimension can be, so it's time to define Hausdorff dimension. Actually, who knows what Hausdorff measure and Hausdorff dimension is? Okay, quite a lot, but not everyone. So quickly, let's recall the Hausdorff measure and Hausdorff dimension. Oh, I need more chalk. Okay. So we have a subset of Rn, and we want to define a Hausdorff S-dimensional Hausdorff measure. We cannot define that immediately. First, we will define a pre-measure or something, which would be the natural thing, but unfortunately there is some extra stuff we have to make. So we want to cover A with a countable sequence of sets, and we want to add up the S powers of the diameters we take the infimum, so we take every possible covering and we want to take the infimum of these S powers. So this would be the natural guess for Hausdorff measure. Unfortunately, this wouldn't be a measure, so we have to require that every diameter is less than delta, and this way we get something that depends on delta. This is monotone in delta, so the S-dimensional Hausdorff measure is the limit as delta goes to 0 of this. Okay, so this is the S-dimensional Hausdorff measure. This is if S equals n, so this is the definition and some properties. So the n-dimensional Hausdorff measure is constant times the Lebesgue measure. And this constant, of course, depends on n. This corresponds to the volume of the n-dimensional ball. And the other, okay, so this is the measure. How will we get dimension? We get dimension the following way. So we fix our set A and we calculate its S-dimensional Hausdorff measure for different S. If S is small, then we see that this is infinity. If S is big, then this is 0. And what turns out that the supremum of those numbers where it's infinity is the same as the infimum of those numbers where it is 0, and this number is called the Hausdorff dimension of A. Okay? And in this dimension, the measure can be 0, can be infinite, or can be something finite. Okay? So this is Hausdorff dimension. And also, I will talk about Minkowski dimension. Yeah, so for example, this set has Hausdorff dimension 1/2, and this set, which is the product of two of those, has Hausdorff dimension 1, and its one-dimensional Hausdorff measure is finite. And now you can see why I was talking about these coverings. So these coverings show that it is finite. So this is a concrete covering, and if you take the sum of the 1's power of the diameters, you get some constant, √2 as far as I see. Okay, and the Minkowski dimension or box dimension defined the following way. We have our set, some bounded set A. It makes sense only for bounded set, and we take a sequence of grids. So this grid length is, say, 1/k. And then we count the number of squares. So let nk A is the number of squares that hits A. And then what we expect, that if a set is S-dimensional, then the number of squares will be roughly k to the time k to s. This is what we expect, and then this is why we take the logarithm of nka and we divide it with the logarithm of k and we take the limit. This limit either exists or not, so if we take the lim sub, then we get the upper Minkowski dimension. If we take the lim, then the lower Minkowski dimension, and if they agree, then we get the Minkowski dimension. It's also called box dimension because this corresponds to this box picture. Okay, so now we understand this, and now I can ask. So now we can state the Kakeya problem, which asks what is the Hausdorff dimension or the Minkowski dimension of a Kakeya set. Oh. Yeah, I was afraid that I can tell much less than I wanted, and this is what exactly happens. So, okay, so let me write the Kakeya conjecture. So the Kakeya conjecture says that the Bezikovich set, any Bezikovich set in Rn, so any set that contains segments in every direction has, well, there are two versions, either Hausdorff or Minkowski dimension n. So a Bezikovich set can be small in measure but cannot be small in dimension. And I should have mentioned that the Hausdorff dimension is always less or equal than the Minkowski dimension. The lower Minkowski, which is bigger, which is less or equal than the upper Minkowski, which means that stating that this is n is stronger statement than stating that this and this is m, obviously. Okay, and okay, what is known? So the most interesting partial result is due to Davis. It's about 1970 something, who says that in the plane this is true. And in higher dimension, so let's see the n equals 3 case. There life is much harder. So in Burgen around 1990 proved that this is at least 7/3, and for the Hausdorff, actually for Bohl's dimension, and Tom Wolf proved in 1995 5/2. Sorry, 5/2. 7/2 will be a bit too much. And then came three brilliant young people, Katz, Laba, and the famous Terry Tao in 2000. And they could improve this. Well, it's a paper of 50 pages and works only for Minkowski dimension, and the improvement is 10 to the minus 10, so some epsilon. Okay, for Minkowski. That time I was in the US, and Ned Katz gave a talk at the university where I was about this, and then he said that, well, it wasn't written up that time, and he said that he believes that with more technical issues it works for Hausdorff dimension, but even it was 50 pages for Minkowski dimension, and I don't know why they gave up, but they never claimed officially that they know they can beat this. And actually, at this point, I was very young, very optimistic, and I thought that everyone else is absolutely stupid. And I mean, these guys are okay. These are good names, but they are stupid. I mean, this doesn't converge to 3 at all. So I said, okay, I will just find a counterexample, and I will disprove the conjecture. And then I wrote some grant application and thought, okay, first of all, so all these I find very interesting. These people were interested not because they like geometric measure theory, but because they like harmonic analysis. I will tell you a few words about the connections, but for me, it was interesting in itself, and I thought that, okay, I will be able to show a counterexample, and then I wrote a grant application, and then, okay, I started to read something about the background, why other people are interested in this question. I needed no motivation because I think these are very interesting questions, and it turned out that all these, this problem is connected to many open questions in different areas. The most important open questions in harmonic analysis, but also open questions about Dirichlet series and many other things. And surprisingly, so that time Tao proved some deep results that says that all those conjectures would imply this conjecture. So if I am that clever as I hoped that time, I'm not that optimistic anymore, then a counterexample would disprove immediately many conjectures which I cannot even understand. Unfortunately, I wasn't able to prove a counterexample. Still, actually, I'm not convinced but that the conjecture holds. Right now, what I believe is that this is probably true, and this might be false. So an ideal paper of myself would be proving this and disproving this, and it can be a good project for you as well. Okay, this is roughly the first half I wanted to talk about, but my time is over, so now I will just tell you a few words about what are those things that I couldn't tell you. One thing is a proof of this Davis result, because Davis result can be proved using the dual approach. Because okay, I can tell you roughly the argument. So suppose we have, okay, now for simplicity, suppose we have a Bezzecovich set with lines. Then, if you take the code set, then we know that to the x-axis, the projection is everything. So the code set has projection 1. And now we use another wonderful projection theorem of Marstrand, which says that if we have a set in the plane with given dimension, then almost all projections has the maximal dimension you can imagine. So if this set has dimension at most 1, then almost every dimension is the same as the original dimension of the original set. If it's bigger than 1, then of course it will be 1. So then this says, because this set has dimension at least 1, almost every projection has dimension 1, which means that almost every, so this is the code set. So if you go back to the Bezzecovich set, then almost every vertical intersection has dimension 1. And then it is true that this implies that the whole stuff has Hausdorff dimension 2. So this is the proof of this. If I had time, I would tease you with checking what's wrong with higher dimension. Because in higher dimension, you can generalize this, and the only problem is everything works very nicely, but then we have many projections. So almost every projection in higher dimension is a several dimensional family, but these slices is just a one-dimensional family. So almost every is not enough for us. And there was nothing about personal stuff and personal results. So I also want to tell you my conjecture, which is related to that. My conjecture is, so now I think I won't write anything more because our time is over. My conjecture is much simpler. My conjecture is the following. Suppose we have a collection of line segments in Rn. And now, at some point, let's extend every segment to a full line. Then we get a larger set. And so let's take the Hausdorff dimension of the first set, of the union of the segments, and let's take the Hausdorff dimension of the full lines. And my conjecture is that these two Hausdorff dimensions are the same. So extending segments cannot increase Hausdorff dimension. Well, this seems just vaguely related, because if my conjecture is true, then it shows that taking segments or taking lines doesn't make a big difference. But the surprising thing is that the connection is much stronger. The connection is that my conjecture would imply that the Hausdorff dimension is at least n minus 1, which would be much, much better. Right now, the best estimate is some constant times n, one constant is about 0.6. And that this is true. So my conjecture is stronger, this segment extension conjecture is stronger than the Minkowski. So then you would think that, okay, but who believes that extending segments doesn't improve the dimension? Well, of course, I cannot prove it, because if then I would have talked about that. But I can prove my conjecture in the plane. So in the plane, this is a theorem. In the plane, if you have a collection of segments, if you extend them into full lines, that doesn't change the Hausdorff dimension. So then, after this, one might hope that then it should be true in higher dimension as well, which I cannot prove. And now you might ask that, okay, so can we apply my result in the plane to get something new in higher dimension? Well, so because I can prove that my result is true in the plane, and this implies n minus 1, my result implies that any Bezikovich set in the plane, any Bezikovich in the plane has Hausdorff dimension at least 1, which isn't that strong. Okay, but I mean, if you have some ideas how to prove my conjecture, do it, and then you will prove this very, very important conjecture. And if you can disprove it, if you disprove my conjecture, that would be interesting only for myself. So if you want to disprove something, then disprove the original one, and then you will do something that you cannot even understand. Why? I mean, they cannot even understand the consequences. Okay, I'm sorry for talking too long, and I am even more sorry not telling you all those nice things I wanted, but that's all I could tell you. Thank you.